Okay, so here we have a problem where we're absorbing ammonia from an airstream using water. So in this case, the ammonia is going from the airstream to the water at a total pressure of 130 atmosphere, and we have this flow rates and compositions, blah blah blah, and we're tasked with finding L min, L, and N, and we know that the solvent rate is 1.5 times L min. We have the equilibrium data here, and the units of the equilibrium data are quite strange. So it's provided to us in terms of partial pressure of ammonia, in terms of weight percentage of ammonia per 100 weight of H2O. So this is a bit of an unusual equilibrium, but we're going to have to deal with it. Now, first of all, since this is an absorption or stripping problem, and the entering vapor is 17.2 weight percent ammonia, we know that we're going to have to use weight fractions, weight ratios, instead of weight fractions. So the first thing to do is to calculate the flow rates, but in terms of the inert substance in the flow rate. So that means that everything that's not NH3. So let's start. So we have V, which is 1050 kilograms per hour, and we know that 17.2% of that is ammonia, so it is going to be equal to this times 0.172, and then this is also in kilograms per hour. This means that the remaining inert flow rate is going to be equal to V minus NH3. We also know that the recovery rate of the ammonia is 98%, so that means that the removed ammonia is equal to 180.6 times 98%. There we go. And so that means that in terms of remaining ammonia in the stream, so remaining we have 180.6 minus 98. Okay, so now that we've determined the flow rates, we can go ahead and calculate the mass ratios. So the final mass ratio is quite simple. It is equal to, by definition, it is equal to 3.6 divided by the inert flow rate, which is 869. That gives us this. So exit mass ratio. Yep. We also have the initial mass ratio, which is going to be equal to 180.6 divided by the inert flow rate. So 0.20. And let's look at the water ratio. So we know that the water, when entering, is pure, which means that the initial water ratio is equal to 0. We know that the exiting water ratio, well, we don't know the exiting water ratio, and we can't know that because we don't know the flow rate. Okay, so the next step now is to draw out the equilibrium graph. Now in this case, it is a little bit complicated because of the unusual units that this equilibrium relationship is written in, but let's do it. So first of all, we have this weird weight ratio, and this is actually what we want. We just need to divide by 100 to get the useful value. So we're going to take this and divide by 100, and do that for the entire range. And this is our liquid mass ratio, which is denoted by the capital X. And so now our equilibrium is given to us in terms of a partial pressure. So how do we convert this partial pressure into some sort of useful value, such as a mole fraction or a mole ratio or a mass ratio? Well, the key is to look at Raoult's law. So Raoult's law says that the vapor mole fraction times the total pressure is equal to the liquid mole fraction times the partial pressure. Now, the total pressure is simply 760 millimeters of mercury times 1.3, which gives us 988. So we can go ahead and find the pressure ratio here. So this is going to be equal to the partial pressure divided by the total pressure. And let's do that for the entire range again. Now, here lies the issue. We have mole mass ratios, but we need to convert this into mole fractions in order to calculate the equilibrium. So let's do that. So first of all, we need to first convert this mass ratio into a mass fraction. And we can do this by simply taking this value and then dividing it by the same value plus 1. So we're simply just inverting the formula in a sense. So let's do that for the entire range, and then we get these values. Now we need to calculate the mole fraction of ammonia in the liquid phase. So we can do that by performing a simple dimensional analysis. We know that, first of all, there are two components. There's ammonia and there's water. The molar mass of ammonia is 17 grams per mole, and the molar mass of water is 18 grams per mole. This means that we can calculate the mole fraction by taking the mass fraction of ammonia and dividing it by 17, and dividing all this by, once again, the mass fraction divided by 17 plus the mass fraction of water, which is 1 minus the mass fraction of ammonia, and dividing that by 17. So we essentially just divide all the mass fractions by their molar masses, and then we get our result. There we go. So now we can calculate the equilibrium, or the vapor mole fraction, in other words. So this would be Y mole. And from the equation, the vapor mole fraction is simply the liquid mole fraction times the ratio that we calculated earlier. So let's do that. Now we have a result. We need to convert this back into a mass fraction, and we can do that by doing the opposite of what we did previously. So we can take this and multiply it by 17, and then divide it by the vapor mole fraction times 17 plus 1 minus the ammonia mole fraction times 18, and this gives us our value. So once again, we extend that to the entire range, and we convert this into a mass fraction, which is denoted with a capital Y. So this is equal to this divided by 1 minus the same value, and then we have our result. Now that we have the mass ratios, we should draw a graph. So let's do that. Let's create a scatter plot. And now the scatter plot is going to have the liquid mass ratio in the x-axis and the vapor mass ratio in the y-axis. So let's just do that real quick. And then let's create a line just for clarity. So you can see here that we have our equilibrium line. It's a nice curve. And now the next step is to find Lmin. So to do that, Lmin is found from the slope of our operating line. So what is our operating line going to look like in a minimum flow situation? Well, it's going to pinch the equilibrium line at some point. So before we start tracing the line, we know that it has to pass through a specific point. So it has to pass through the concentration of the vapor and liquid streams at the bottom of the column. So the mass ratio at the bottom of the column is going to be the exit mass ratio for the vapor, and the water mass ratio is going to be 0. It's going to be the initial mass ratio. So this would be the top of the column, actually. My apologies. And I also seem to have mixed these up, so this would in fact be the correct positions for these values. So as you can see, it's a bit hard to tell, but it is clearly slightly above our equilibrium line, so that means that we are indeed in the stripping problem. Now, we have to figure out where this operating line intersects with the equilibrium line. Since the operating line is above the equilibrium line, it's quite clear that it's going to intersect at the very other end of the column. So it's going to intersect wherever the column reaches a vapor mass ratio of 0.277. So in that case, that means that it's going to intersect around this point here. So just for the sake of clarity, we're going to reduce the range of this graph slightly. There, just so we look at we're able to look at the relevant area. So if we take this line and we trace an operating line so that it intersects with the equilibrium line at the y value of 0.2077, it should look something like this. And of course I'm guesstimating here, but it does look like, and we can also add some grid lines just to make it a bit easier. So it does look like it intersects the equilibrium line around the point 0.207, and in terms of the x-axis, it looks like it intersects around the point 0.64. So let's guesstimate that. So let's say that the exit water ratio is equal to 0.64. So now we know that the slope of the operating line is going to be equal to L over V. So once we calculate the slope, we can find L min. So the slope is simply the difference between this point and this point. So it would be equal to this minus this, the two y values, divided by this minus this. And it gives you a slope of 0.318. We know that L min, so we know that the slope is equal to L over V, which means that the slope times V is equal to L min. And there you have it. So L min is equal to 334 kilograms per hour. Now, we know that in our scenario, we want L to be 1.5 times the minimum solvent flow rate. So we're going to do that. We're going to do L is equal to L min times 1.5. To calculate the operating line, we know that the operating line equation is going to be equal to y equals L over V times x plus yn plus 1 minus L over V times xn. So let's just create a new series here. So the x-axis values can be completely arbitrary. So we know it has to go somewhere from 0 to 1.6 is 0.6. So let's do something like that. So 0.1 all the way to 0.6. Now, so the y value is going to be equal to x value times L over V plus yn plus 1. And yn plus 1 is going to be equal to the exit mass ratio minus L over V times the initial water ratio. And there we go. And everything here needs to stay put, so we're going to do that. And then we get our value. So let's just add this series. And there we go. We have our optic line, and actually let's make it connect to the origin. So now that we have the operating line, we can simply use McGill analysis in order to find the number of stages. Okay. So as always, you start from your point of interest. So at y equals 0.2077, and then you simply draw the staircase like this downward until you reach the end. And there we go. So just keep in mind that when we draw a McGill analysis, we need to start from the operating line and then proceed towards the equilibrium line. So since we're doing an absorption problem, we draw like this instead of starting from here and stepping down like that. So in this case, the number of equilibrium stages is equal to the amount of times we touch the equilibrium line. So this would be 2.5 stages. And that concludes the problem.